Today, we are talking about infinite integrals, which is pretty exciting in itself, but we're not looking at any old infinite integral. We are looking at the big daddy of infinite integrals, the Gaussian integral. We're going to integrate from minus infinity to infinity the function e to the minus x squared. The reason this is such a big deal of an integral, it's often referred to as the Gaussian, named after Gauss, very famous mathematician. The first time you come across integration, you see this thing, you see what it's equal to. I won't give it away just yet, but you'll recognize it. You see the answer and you just immediately want to know, how on earth does that work? And today, I'm going to go through all the steps, we're going to figure it out and show that amazing result. So, minus infinity to infinity, e to the minus x squared with respect.
Wow, you're...
I'm so excited, I've torn the paper. Right.
I've never seen that happen before. Wow.
Literally, contain my excitement. Okay, so we're going to figure out this integral. A good place to start with any integral is to think about, what are we actually doing? Like, what does this function look like? Why does it even make sense to consider this from minus infinity to infinity, right? Because for some functions, that's going, you're going to get infinity, and then it's all nonsense. So a good place to start with this one is think about its shape. And if you haven't recognized it or you don't really know what's going on yet, this might jog your memory. So this function is going to have the value 1 in the middle. So when x is 0, we get e to the 0, which is just 1. And then it kind of decays as we go in both directions. So it creates this bell-shaped curve, this Gaussian curve. That's where the name comes from. There's also a clue there as to what the answer is going to be, but we will wait till we get there. So we have this bell-shaped curve, and what this integral is asking us to do is work out the area under this curve. So anytime you're dealing with an infinite integral, it's a really good idea to draw a picture and actually make sure you're going to get something, or it feels plausible you could get something that isn't just infinity. Because if I have something that's just increasing like this and I'm going under this, I'm just going to get infinity. Not interesting. So we need to check it's going to give us that finite answer. So now that we've established it's going to converge, it's going to be finite, well, it feels like it might be, let's actually figure out what is it equal to.
You told me it's finite, but presumably these ends, these tails of the bell, are never going to touch the line. They're never quite going to get there.
Yeah.
But it will give me a finite number.
It will. I haven't proven that, but by drawing the picture, it feels plausible. Like you're going off vibes for sure. I've not done anything here that proves this is going to be finite. But as I say, if I take the really extreme example, right, this is like e to the x, and I do this from minus infinity to infinity, that's clearly infinite. This just keeps getting bigger and bigger and bigger. There's no way this area is not going to be as big as anything. But here we have a chance. It's decaying in those tails. Definitely doesn't touch, but it is getting small pretty quickly. So that's going to give us a chance here that it could be something finite, and that's what we're going to see. To do this, we cannot integrate directly. And this is why it's one of those that bothers anybody who does integration and sees this for the first time. Because normally you have a function here, you want to do something called the reverse chain rule and kind of reverse engineer what it could have come from, what could it be the derivative of. But here, again, if you've seen this before, you'll know that it doesn't work. And so we have to actually employ a completely different technique. And this is why it's such a fun result, because we're going to do something completely different. So we're going to label the integral I for integral, very creative. And we're actually going to consider I squared. Now, this is one of those where once you see it work, you're like, this is beautiful. But I don't know how you would come up with this, in all honesty. But it's one of those, right? Some mathematicians in the past, very clever people, have come up with this approach. So we're going to square it. So what does that mean? Well, it means we've got the integral, and I'm going to say this is now x from minus infinity to infinity, e to the minus x squared with respect to x. And then we're going to multiply it by itself. But just to emphasize this is a different integral, I'm just going to relabel my variable as y. It doesn't matter. It's the same thing. This is a dummy variable, but I'm just going to call this y. So now I have a result for I squared, but I can actually combine that into a double integral. So x is going from minus infinity to infinity, y goes from minus infinity to infinity, and now I've got an e to the minus x squared times an e to the minus y squared. When you multiply two numbers together to a power, you add the powers. It's the same number. So I get e to the minus x squared plus y squared, and now I'm integrating dx and dy. So this is now I squared, and at this point it might not look any easier, But we're going to do some more clever maths and actually get something that we can integrate. But as usual, I need more paper. So now we have an expression for I squared. We have this double integral, which, if you've never seen them before, potentially is terrifying. But if you think about what integration actually is, so I said here, this is giving us the area under the curve. So now when we do a double integral, we're kind of doing the same thing. We're working out an area underneath like a 3D surface. What we want to think about now is over which region are we integrating? So at the beginning, we went over the whole line. We went from minus infinity down here up to plus infinity, and this was for x. But now we've got x going from minus infinity to infinity and y going from minus infinity to infinity. So we have some kind of 3D surface, and we're actually integrating it over the whole plane, all of x and all of y. It's not just infinite, it is a doubly infinite integral. Minus infinity to infinity, minus infinity to infinity, 2 times over. So we now want to think about, well, rather than working in x and y, and this is the clever part, can we change the way that we describe the plane? So again, Cartesian plane, we sort of have all of these lines which represent different values of constant x, and similarly for the negative. And then for these horizontal lines, these are constant values of y. And this works perfectly because if I have a point here, I can specify the xy coordinate of that point. Rather than thinking of this in terms of x and y, we're going to set up a different coordinate system. And this coordinate system, we're going to measure the distance to the point from the center, we'll call the distance r, and then we're going to measure the angle, which we'll call theta, with the positive x-axis. And it's always with the positive x-axis. That's just a decision we've made, a convention. The reason this is going to be helpful is I can actually describe any point in the plane. I could use x and y, but I can also use r and theta. I can also describe what is the distance to that point and what's the angle. And that's going to give me actually a unique way of specifying that point. So rather than going from minus infinity to infinity with x and minus infinity to infinity with y, I can now say, well, how do I cover the whole plane? So I could be really close. So r could be really small. So r is going to start at 0. Could be really small as I'm close.
A really short walk.
Exactly, a short walk. But then I could also be really far away. And so it's going to go all the way to infinity, right? That's giving us this kind of infinite distance, potentially. And then for the angle theta, well, once I know how far away I am, then I also need to know, I'm actually going to get a circle, in fact. I also need to know what angle am I at. You know, maybe I'm over here, and so I've got a different value of theta. So if I specify the distance and I specify the angle, which is going to be the full 360 or 2 pi, we prefer to use radians. So I can go all the way from 0, how far round do I go, fix that angle, and once I know the angle, I then walk out the distance r. So it's uniquely giving you every point in the plane, just like we can uniquely give any point through x and y. So now, instead of going from minus infinity to infinity for both x and y, we can instead describe the whole region we're integrating over using this 0 to infinity on the distance and 0 to 2 pi on the angle. So all we have to do now is figure out, well, how do we change this integral involving x and y? We have to figure out, well, what do x and y look like in terms of r and theta? We change variable, we're changing coordinate system, and hopefully we'll get something that might look a little bit nicer than what we have right now. So if we go back to our general point, xy, I'm going to make this a triangle. I'm going to put a right angle there. And now I know the hypotenuse, the diagonal line is distance r, and I know that the height here is given by y, because that's my vertical coordinate, and I know this horizontal distance is given by x, my horizontal coordinate. So from this picture, and using simple trigonometry, I can just say, well, cos of theta is, remember this, adjacent over hypotenuse, so that would be x over r. So x over r is cos theta. And similarly, I'm going to get sine of theta is going to be the opposite over the hypotenuse, so y over r. So this now means, sort of rearranging, that x is r cos theta and y is r sine theta. So this now tells us the relationship between x and y and what happens when we turn that into r and theta. So we want to substitute this into our integral.
It's like our exchange rate.
It's exactly that, yeah. Previously, we went the whole plane. So how do we describe the whole plane? We know it's r going from 0 to infinity, and it's theta going from 0 to 2 pi. So suddenly we've lost the minus infinities, and only one of them is infinite, which feels like we're making progress. And now our function here is e to the minus x squared. So that's r squared cos squared theta. And then it was plus y squared, so plus r squared sine squared theta. And then we've got this dx dy. I'll come back to that in a moment because there's something going on there. But now we've got an r squared term we can pull out of the bracket, and you've got cos squared plus sine squared, which is 1. Classic trig identity. So what we've really got here is r goes from 0 to infinity, theta goes from 0 to 2 pi, e to the minus r squared times cos squared plus sine squared, which is always 1. And then we still have this dx dy term. So I haven't changed this because that is going to require a little bit more work, because we have to think about what does this mean and how do we turn this dx dy into something involving r theta. Once we do that, we then have our full transformation. We've converted to a different currency, to use Brady's exchange rate analogy. And then hopefully we can actually do the integral and get the answer.
Paper?
Yeah. To figure out what does this mean, dx dy, we sort of go back to the initial definition of an integral. And again, thinking of it as the area under a curve. So dx here means let's take a very small distance along the x-axis, and then what we're going to do is actually going to let that tend to 0, because as we take smaller and smaller slices and then add them all up, that's how we get the area. It's as you make these smaller and smaller and smaller, they look like very thin rectangles. And then we just add them all up, and that's what's going to give us the integral and give us the area, give us the answer. So what's happening in 2D now, it's very similar. But instead of just having a single slice, we've now sort of divided the plane up into these tiles. And if we focus in on one of these tiles, this is a small piece of area, which we can call dA. It's a small bit of area, just like this was a small bit of the x-axis, a small slither of our function. This is a small square underneath our 3D surface that we're actually trying to integrate. So we can say this has width dx and height dy. Again, emphasizing it's small. But we've now moved to polar coordinates. That's what these are, r and theta, distance and angle, they're called polar coordinates. So a small piece of the plane is no longer a rectangle, because we've actually created almost like a spider web shape for the Cartesian plane. So rather than having all of these little squares and rectangles added together, what we've got is all of these different circles as we change the radius, and then within each circle, we've got different angles. So it really does look like, to me at least, a spider web or a dartboard. And if we focus on one of these shapes, so if I take this segment here, it's got curvature. It's no longer a simple square. So it's not just dx times dy, but we can figure out what it is by drawing a much bigger picture. So coming away from the origin, we have something that looks like this, and then we're kind of out here. What we want to do is think about a small change in one coordinate and a small change in the other. So we say this one is the radius, the distance, let's call that r. So then what I've gone here is a little bit further, so this is r plus a small amount. Just a little bit further out than where we started. This is definitely exaggerated. And then also, we've increased theta a little bit. So to get to this line, we've kind of gone through some angle to get there, and then we want to do a little bit extra, d theta, just a little bit further around. So we've like fixed our r, and we're like, let's go a little bit further around that clock dartboard, a little bit further around, and that's going to be a d theta little segment. So all we need to know now is what's the area of this, because these will be our dA, which is equal to dx times dy. That's what we sub in our integral and how it's going to all come through. So we're working out the area of a sector. There is a formula for this, but it sort of makes sense to see where it's come from. We can think of it as saying, well, if I had the whole circle, then I would have pi times the radius squared. That's the area of the circle. But I've only got a fraction of it, and I've got some amount of it. So I've got d theta out of 2 pi. I've just got part of the circle, and then multiplied by the area. So the area up to the edge would be pi times the radius squared, which is r plus dr squared. But what I've actually calculated here now is this whole bit. It's like the slice of pizza. But I don't want the whole thing. I want to get rid of this inner piece.
You just want that thin crust.
Exactly. Yes, just want the pizza crust. So we're going to subtract off the inner bit, which is the same factor d theta out of 2 pi, but now it's pi times r squared. So we subtract that off. So again, it's this bit is the red, and then we subtract off this bit times this, which is taking away this part. So we're just left with the bit that we want. Now, what's this equal to? And this is the magic. Well, when we are doing the integral, as I mentioned here with the area, we're letting these go thinner and thinner and thinner. So here, we're letting d theta go smaller and smaller. It's tending to 0. dr is tending to 0. So these terms are getting tiny. So we actually only want the biggest term that we're going to be left with. And that's important to remember. So if I simplify this, we're going to lose the pi. Inside this bracket, well, you're going to get an r squared plus a 2r dr plus a dr squared, and then minus the r squared. So we lose the r squared term. And so what I'm left with is actually just d theta over 2, and then we've got 2r dr plus dr squared. But now, if we compare the size of these two pieces, these two terms, this is really, really small, and this is really, really small, but r isn't. R is like an actual number. So this is like doubly small, so we just ignore it. We just say it's 0. We throw it away because we're taking that limit. So what we end up with then is that our area piece, dA, for the spiderweb, the dartboard, the pizza, whatever we're calling it now, 2's cancel, and it's r times dr times d theta. So this is now what we're going to stick back in that original integral, and we're going to get that magical result. So now we can fully go back to I squared. So we'd already established we're going all possible distances, all possible angles. We have e to the minus r squared. We simplified that. And now our little dx dy, that small piece of area, is represented by r times dr times d theta. Now this, if you're new to integration, this might not feel any easier than where we started, right? And but, there's a big but, and this is why I think it's so beautiful. This r term coming in, this is the game changer. This is like the magic trick, the secret like card you have played to basically ace the whole thing. So the key thing is, before we had e to the minus x squared. And there's a problem here, because if you differentiate this function, you take its derivative, what you do is you bring down the thing, you differentiate this thing at the top and get back the exponential. So if you want to go back and integrate up, you need this x outside of your exponential. And we didn't have it. But now, thinking about things in terms of r, we've got it. That's why it's so key, because it turns out that the integral of this, it's just the derivative of a function that we can figure out. So if I do the derivative of e to the minus r squared, I bring that down to get minus 2r, and then it's that e to the minus r squared. And this is what we've got. We've got the r here. All right, we've got a minus 2 factor floating around, but we don't care about that. So this thing actually has an exact integral that we can now write down. We can just do the integral without worrying about everything else that's happening. So what do we get? So I squared is, I'm going to do the integral with r, so we've still got theta there. Can't do anything about that. But the r integral is just going to be minus e to the minus r squared over 2. So I've just multiplied through by minus a half to get rid of that 2, and we'll get our function. And then I have d theta, and I have to substitute in my limits, which are 0 to infinity. So this tells us now, substitute in r equals infinity. So e to the minus infinity, we saw this in the graph at the beginning, it's 0. If we go, it never gets there, but if we go all the way to infinity, technically we are tending to infinity rather than subbing in infinity. But it's going to give you 0, eventually going all that way. So that term disappears, and then it's minus the second limit, and when you sub in 0, you just get 1. So minus a half gives you a half. So this is now just, we haven't done theta yet, but we've just got a half d theta. So now you just say, okay, so this is saying basically, think of theta as x if you want, whatever variable you want. It's just what's the area under a curve that's constant a half from 0 to 2 pi. Well, that's just pi. You just do that integral straight away. Or if I want to fill in the steps, you say it's theta over 2, you integrate up, and then you go from 0 to 2 pi. So you just sub it in and you will just get pi. So as if by magic, we've shown that the square of the integral we wanted to do is equal to pi. So now you just say, all right, so then that means the thing I started with is the square root of pi. And that is the Gaussian integral. That is the result of the big daddy of integrals. So now we know the area under this curve this kind of Gaussian curve, this bell-shaped curve, we now know this area here, from minus infinity to infinity, this area is equal to the square root of pi. Because what else would it be? It's always pi. Always pi.
There you go. All right, I'm with you. Thanks for watching. For more videos from Tom Crawford and to learn more about what he's up to, check out the links in the description and the comments. Also, thanks to our Patreon supporters. These people go the extra mile to make our videos possible. Just some of them are listed here on the screen, and if you go to the Numberphile website, you can see a full list of everyone. Our thanks, and see you in the next video.